In this video, we're starting the next unit on circles. And basically in our circle unit, we're going to be thinking about these topics. How the equation of a circle relates to other algebraic equations. A proportional relationship exists between circles and pieces of circles. And the question, why do we need to know how to graph circles? So as we go through this unit, these are the things we need to be re-examining and always going back to. In this first video, I'm going to give you a lot of vocabulary, so please make sure you take the time to write down any new definitions that you don't already know. And if I go too fast, that's why you have a pause button, so please do that if necessary. So first of all, what is a circle? We know that a circle is a set of all points in a plane that are equidistant from a given point. And the center of the circle is that point from which all points of the circle are equidistant. The radius is the segment from the center of a circle to any point on the circle. And a chord is a segment whose endpoints are on a circle. And I will be showing you a diagram of all of these terms in just a minute, so you can have a visual with your definitions. A diameter is a chord that contains the center of the circle. A secant is a line that intersects a circle in 2 points. And a tangent is a line in the plane of a circle that intersects the circle in exactly 1 point. So secant crosses the circle in 2 points. A tangent only touches the circle in 1 point. So let's look at what all of those look like in a diagram. So here we have our circle. The red dot is our center. And then we have this green segment right here is the radius. Notice the radius goes from the center to a point on the circle. We have a diameter and we have a chord. Notice a chord can be any segment that that connects 2 points on the circle. So here is a chord here, and then the diameter is also a chord. But what's specific about a diameter is that it has to go through the center. And then we talked about the secant line. A secant is a line that goes through the circle in 2 points. So you see those 2 green dots there. And then a tangent line crosses the circle exactly once. So notice how it looks like it's skimming the surface of the circle. And then where it touches, that's where we call the point of tangency. All right, so that's where all of those terms fit into a circle. I need you to know all of those very well, because we'll be talking about all of those later when we talk about those relationships within a circle. So in the next section, 10.2, we're talking about arc measures and angles. Okay, so a central angle. So we know what an angle is, but a central angle when we're talking about a circle is a vertex whose center is on a circle. So you see this arrow pointing to P. So P is the vertex of the central angle, and there are several central angles here. And I'll trace them out for you here. So I have angle APB. That is a central angle. I have angle BPC. That would be a central angle. And I also have angle APC or CPA. Those would also be central angles. What I need you to know about central angles is that they have degree angles, degree measures that we're very familiar with. We know that there's 360 degrees in a circle. So if this angle right here, let's say this angle right here is about 100 degrees. Okay. That central angle is going to have the same degree measure as the arc. So let's talk about what is an arc. So, that's not what I meant to do. A minor arc is formed by a central angle that is less than 180 degrees. So you can see this red arc right here. That is what we would consider a minor arc. This This part right here from C to B, that would also be a minor arc because we were just saying that that has less than 100 degrees. This arc is always going to be the same as its central angle that creates the arc. So the central angle that creates this arc is PBPC. BPC is 100 degrees, and so this arc BC is 100 degrees. If this red arc AB, that is created by the angle APB. So if this arc angle right here, let's say that was 105 degrees, then that minor arc from A to B is also 105 degrees. Okay, so that's what we mean by an arc, and a minor arc is simply one that has a measure that is less than 180. Okay, a major arc is formed by a central angle that is greater than 180. So the major arc, let's say I went all the way from B all the way to A. So that is formed by this arc right here. So we know that this straight angle is 180, and then this is 100, so this whole arc would be 280 degrees. Okay, and then obviously then this 105 is not correct because we know that has to be 360 degrees. But I was estimating there, so we can change that if we want. So all I'm trying to point out to you is the difference between what we call a major arc and a minor arc, and how we know how many degrees each of those arcs is. A semicircle is an arc whose endpoints are diameter of the circle. I think we understand a semicircle is half the circle. So if I was just talking about the arc from A to C, that is just this part from here to here. We know that's 180 degrees, so that's a semicircle's 180 degrees exactly. Okay, so minor arc is less than 180, major arc is greater than 180, semicircle is exactly 180. Congruent arcs are simply arcs that have the same measure. So let's look at these diagrams and see if they have congruent arcs. Okay, so this arc is a semicircle. This arc is a semicircle. So we would say arc WZ, and when we name an arc, we just put an arc above those two letters. And we would say that's congruent to arc XY. Okay, so those are congruent. Notice that I'm not worried about the length of those arcs. We'll talk about arc length later in the unit, but I'm not talking about the distance. Like if you had to walk around the edge of this circle, those would be different lengths that you walked. I'm not talking about that. I'm only talking about the degrees, the opening of the arc. All right, same thing over here. These two arcs both have the same measure of 135 degrees. So that would mean these are congruent arcs. So EF, arc EF, is congruent to arc GH. All right, so that's just how we're going to call those congruent arcs. Now we're going to talk about another kind of angle called an inscribed angle. An inscribed angle is simply an angle whose vertex is on the actual circle itself. Okay, the sides contain chords of the circle. The intercepted arc is the arc that lies in the interior of the inscribed angle and has endpoints on the angle. So you can see in this diagram, this red angle is an inscribed angle, and then this blue part of the circle is what we call the intercepted arc. Notice how the blue part is inside of the red angle. Also, you might remember when we were talking about inscribed triangles that those were triangles. Like if I put points here, here, and here, and I joined those 2 points. The inscribed triangle is the triangle where all vertices are on the circle. Okay, so that might help you with that inscribed angle. Remember the difference between an inscribed angle versus a central angle. Okay, remember that a central angle is an angle whose vertex is on the center. So notice that the center of the circle is not drawn, but I drew that in there. And that would be a central angle, that green one. Okay, so green is central, red is inscribed. Here are some different versions of inscribed angles. So you can see that an inscribed angle, one of the sides of the angle can go right through the center, like in this red one. The both sides of the angle could straddle that center, so like in this green one, or they could be on one side of the center or the other, so like in this blue one. So there's lots of different ways those inscribed angles can happen, but notice in all of these situations that the vertex is actually on the circle. Okay. So just to give you an idea of what you might see in future diagrams. So here's a theorem that you need to know. The measure of an inscribed angle is equal to half the measure of its intercepted arc. So whatever that arc is, okay, so let's say in this diagram we call that, oh, I don't know, let's call that 80 degrees. This angle, this inscribed angle, has to be half of that. So this inscribed angle has to be 40 degrees. Okay, so let's do some examples here. In this example, we have this arc right here is labeled as 140 degrees, and they want us to know what is the measure of angle XYZ. Well, notice that angle XYZ is an inscribed angle. The vertex is on the circle, so it would have to be half of this angle. So half of 140 would be 70 degrees. And then over here, we're going backwards. They've given us the angle measure of angle PSR. Notice that PSR is an inscribed angle. So that means this intercepted arc, PQR, is going to have to be twice as big as that one. Since this is going to half of that, then if I'm going backwards, it has to be twice as big. So twice as big as 80 is 160. So that arc is 160 degrees. Another thing that what kind of follows from that is if two inscribed angles intercept the same arc, then those angles are congruent. So look at this diagram for a minute. You see how both of these angles have the same intercepted arc, this purple arc. Let's say that that was 70 degrees. Well, by the previous theorem, we would have to say that this angle right here is half of that, so this would have to be 35 degrees. And then this angle right here, since that has the same intercepted arc, that would also have to be 35 degrees. So it makes sense that those two angles are congruent because they have to be the same measure. So here's a reason why we use that. Imagine that you're in a theater. When you go to the movies, you want to be close to the movie screen, but you don't want to have to move your eyes too much left and right to see the edges of the picture. So E and G are the edges of the movie screen. And then you're sitting at F. Okay. Your EFG is your viewing angle. So this is your viewing angle. Okay, that's how far you have to turn your head. And you decided that the middle of the 6 rows is your best viewing angle. So if someone is sitting there, where else could you sit to have the same viewing angle so you won't have to turn your head that much? Well, we're going to use that intercepted arc theorem to help us with that. If we were to make a circle, okay, so we would draw a circle that includes these points that we were just talking about. These were the edges. These two were the edges of the movie screen, and this is where that person is sitting. They're sitting in your spot. Well, where else could you sit? Well, all you'd have to do is find another arc, another angle that has the same intercepted arc. So all we'd have to do is maybe find a seat here. This has the same viewing angle, or this one here. So it's very practical, well, if you were going to diagram your theater. But if you think about it, the way you design a theater can help alleviate that. Back in ancient Greece, stages were often part of a circle. So you can see how this is a semicircle. And they were concentric circles. So we would have maximum viewing angles. So we would have good seats all around. All right, so I think you get the idea for your inscribed angles. The other thing I want to talk about is this theorem. An angle that is inscribed in a semicircle is a right angle. So if I had this angle, this is point B, and then this was point A, and this was point C. Angle B is a right angle if and only if AC is a diameter. Why would that be? What's true about a diameter? A diameter has to go through the middle. What is this arc? What is this central angle right here? This central angle right here is 180 degrees, right? So then this semicircle is also 180 degrees. And that would mean that angle B is an inscribed angle. And that means that it's half of this intercepted arc. So half of that has to be 90 degrees. Okay, this is very helpful because we've learned all about the trig and the right angles, right triangles. So if I know that I have a triangle within this circle, then I know it's going to be right triangle if it's a diameter. So there's lots of information we can gain from knowing that a triangle is inscribed with the inside the triangle, inside the circle. Okay, so an inscribed polygon, so we can't just talk about triangles, it could be any polygon, is just a polygon whose vertices all lie on the circle. Okay, so here's just emphasizing the difference between the word inscribed and circumscribed. Inscribed, if you think about what that means, in means it's inside of the circle, so the polygon is the object that's inside of the circle. Circum, that prefix circum means around. All right, so circumscribed is the circle is going around the object. Okay, so that's the difference between something that is inscribed versus something that is circumscribed. Okay, here the polygon is inscribed and the circle is circumscribed. So what do we care about that? Well, if a quadrilateral is inscribed in a circle, then its opposite angles are supplementary. So you can see that this blue and aqua angle, angle A and angle C, those would have to be supplementary. They have to add up to be 180. And then this red and purple angle, angle B and D, also have to be supplementary. Notice that we are not saying that they're congruent. Okay, I don't want you to think that. So we're not necessarily talking about a rectangle or a rhombus or anything like that, like in the previous unit. But we're just saying that those have to add up to be 180. So let's look at these two examples here. Notice here in example A, I have a triangle, and this is a inscribed angle, and this is a diameter. So that would make our intercepted arc is 180. So that means this has to be a right angle right there. So we can say 3x has to equal 90 degrees, and therefore x has to be equal to 30. All right, here we have a quadrilateral is inscribed in a circle. And remember we said opposite angles have to add up to be 180. So x plus 85 has to equal 180. So if we solve for that, we get 95. and then y plus 80 has to equal 180. So then y has to equal 100. Okay, so that's just how those two inscribed polygon theorems work. So I think we're good there. All right, so I'm going to have you work on some practice worksheets and use your notes from this video to help you complete those.